In the last video, we have completed the 6 type of DC bias configuration for our NPN transistor. Today we will see how those configuration can be applied to our PNP transistor and how our BJT can be act as an switch. But before going to the two topics, let me first do a quick revision of the 6 type of model that we read in the last class, because this BJT subject is bits like that. If you will not do any proper revision, then you might forget all the things, all the derivation. Okay, so just see what are the type of configuration that we read, what is their name, and what are the equation that is needed. So at the starting we have read the fixed bias configuration, or that is called common emitter configuration. So in fixed bias configuration, there is a collector resistor, there is a base resistor, and our emitter is grounded and a VCC applied. This is the configuration. And for that, first we found the value of IB, which is nothing but this VCC minus this VB upon this RB. This is the base current, and the collector current is nothing but beta times IB. Okay, and we know the relation between IE and IB is nothing but beta plus 1 IB is nothing equal to IE. That is for the input side. Then for the output side, what we are going to find VCE. Or VCE between collector and emitter is nothing but VCC minus the drop between drop across RC, which is nothing but ICRC. So these are the three equations that we need for this fixed bias configuration. The next one is emitter bias configuration. So in emitter bias configuration, nothing but the configuration is symbol is same, just addition of RE or a emitter resistor across the emitter. So that's why the name is common emitter with RE. Okay, so here also same. First we will find for the input loop what is our IB. Everywhere, every configuration, first we have to find the value of IB. Here the IB is nothing but VCC minus the drop between B and E divided by the two current into resistor, which is nothing but RB plus this is beta plus 1 RE, because the current across the emitter is nothing but beta plus 1 times IB. So since we are writing in terms of IB, here a beta plus 1 term will be multiplied with RE. Then we will find the value of IC, then IE, then VCE. Okay, and here the input resistor that is seen from this side, the input resistor, which is nothing but the across the resistor RE, which is nothing but beta plus 1 times RE. Okay, now the third one is voltage divider biasing. So what we are going to do here? Here we are applying two resistor, and the voltage VCC will be divided into across two resistor R1 and R2. Then that will be fed to the base. So here we are using the Thevenin's equivalent. So for that, for this VCC R1 R2, first we are finding the VTH, that is Thevenin voltage, then RTH, then we are connecting this side with a Thevenin voltage plus Thevenin resistance. So the Thevenin resistance seen from this side, from my emitter to base, this side is nothing but 2 R1 R2, these are parallel, because here VCC is grounded. Voltage source will be short circuit, current source will be open circuit. So RTH will be R1 parallel to R2. Then our ETH, that is voltage across this R2, is nothing but VCC into R2 divided by R1 plus R2. Okay, then we will replace this whole circuit by this VTH series with RTH. Then we will find the value of IB. Then the current is nothing but the voltage minus this VB drop divided by two resistor. One is series, here is RTH will come, and one RE is there, beta plus 1 RE. Okay, and then we will find IC, then IE, then VC. So in voltage divider biasing, there are two methods. One is exact method, second one is approximation method. So this is the exact method. So in approximation method, we are assuming that our beta RE value should be greater than equal to 10 R2. If this condition will occur, then we can directly put this voltage VB, and then we will no need to find value of IB, because since we are finding IB, our IB was depend on beta, but we want our circuit should be independent of beta, because beta is temperature sensitive, temperature dependent. So as our temperature will change, our beta will change. As beta will change, our IB will change, and the whole equation will change. So we want a circuit that should be independent of beta. That's why we did some approximation. If this approximation occur, then no need to find all these, only we will find the voltage across the base. VB means base to ground. That is nothing but here also voltage divider rule will apply. VCC into R2 divided by R1 plus R2. Then that is VE. Once we will find the VE, we know the voltage drop between VBE, base and emitter, which is nothing but 0.7 millivolt, 0.7 volt, not millivolt, 0.7 volt. Then we know VBE, we know VB. Then easily we can find VE. As once we will find this value of VE, VE means emitter to ground. Then we can easily find our IE. IE nothing but the voltage divided by this resistance. Then IE, and from IE we can find our IB from this equation, because our beta plus 1 IB is nothing but IE. then from there we will get VC. No need to find, means here IB, no need to find this IB which depend upon I beta, then IC which depend upon IB and beta. Okay, here we are not going to find the value of IC also. Now the fourth one is collector feedback. So in collector feedback there is a feedback resistor that is connected from collector to the base. A RF is connected. Okay, and here the current is IC, here the current is IB, here the current is IC dash. So first, then similar we will find the value of IB, which is nothing but this VCC minus this VB upon this resistor plus RC plus RE, because here is one, because of this resistor will come, this is the input loop. So in the input loop 3 resistors are coming, that's why 3 resistors are there at the denominator. Then we will find the IC, then IE, then for the output loop we will find the VCE. Okay, so this is the configuration, this is the so symbol diagram. Here also RE is there, a feedback is there. Now a emitter follower, or it is called common collector, because here collector is the common terminal. So first we will find for the input loop, that is base to emitter loop. Everywhere the input loop is between base to emitter, and the output loop is between collector and emitter. Then we will find IB. So here IB is nothing but, here as our collector is grounded, similar to the previous one, there is a battery source VCC connected to the each and every collector terminal. But here as our collector is grounded, our a voltage battery source VB that is connected to the emitter, that is minus VB, means it is connected in a reverse way. Whenever we will connect a voltage source, we will connect it like this, positive negative, that means it is VCC, it is connected to the collector terminal, collector resistor. Okay, this is RC. So as it is connected after the emitter terminal, how we will connect? We will connect is negative positive, and since we are moving in this way, we are seeing positive and negative. Then when we are seeing negative positive, then we are writing VCC. As we are now seeing positive to negative, we will write minus VE, because this is emitter side. Now this is emitter side, this is RE. That's why the name negative symbol minus VE, because it is connected in such a way that the negative terminal of the battery is connected to the RE. Okay, so here we will find IB, then IC, then VCE. Then the last one is nothing but a common base. Here base is common, and a loop we will write between emitter and base is the first loop, and the output loop is between collector and emitter, the outer loop. So here we will find the value of IE first. IE is nothing but VEE minus this drop divided by this resistor, and from IE we can get IB. Once I will get IB, then I can easily find my IC. Then for the output loop I will write my VCE. From there I will get my VCE. Okay. So this is all about the 6 type of configuration that we read. Now let's see how this DC configuration can be applied to a PNP transistor. Similar to we read before, and PNP, what is the changes? That our direction of current is changes, that is IE is equal to IC plus IE. Here current will start from emitter and it will reach to the collector and base. And the other thing is the direction of symbol direction. So the circuit symbol looks like this. This is the PNP, means it is pointing in. NP first, it is coming PNP, pointing in, pointing P. And from in I am taking N, that's why pointing in I will remember like this. So it is pointing in. Okay, so here it is the PNP configuration. So the analysis of this PNP transistor follows the same pattern established for NPN transistor. Each and everything that we did for our NPN transistor, for our PNP transistor, we will follow the same method. What are those? First we will find the value of IB, then from IB I will find IC, then IE, then the VC equation. Here will be everything will be same. First transistor, the level of IB will be first determined, followed by the application of appropriate transistor relationship, means IC, IE, then VCE. There is a list of unknown quantity. The only difference sign is, what is the changes? Here it is written as VBE. For PNP it will become VEB. Here it is VCE. For PNP it will become VEC. Okay. Similarly, if you will see the circuit diagram, here I have done one circuit diagram. If you will see the circuit diagram, you will get everything. You see, if I will move from here to here, I will write VBE. And this is positive, this is negative. But as I will write VEB, means this terminal will be negative, this terminal will be positive. Okay. Similarly, you have to think here you see my emitter VEB, means my emitter is coming first, means it is higher voltage. That's why a positive voltage is connected. I am shown positive voltage near emitter. Base, that is coming after that. So that's why the base is negative voltage. So if I will write VBE, it means VB minus VE, means my base is positive voltage. That's why positive sign with VB and the negative sign with VE. So don't confuse between VEB, VBE, just to see which type of configuration is there. If it is emitter PNP or NPN, accordingly we will put the convention and write the loop equation. Okay, so you see now this is the input loop. So for this input loop I will move like this, because my current now is starting from emitter, then it will move to the base, to the collector also. And in all the previous cases my base current was coming, collector current was coming, then these two combined to give me a current IC. But here IE, that's why I was writing first starting from this VCC, I was writing loop equation from VCC. But here I will write my loop equation from here, because my current is moving in this way. So here it is 0 voltage minus current is moving bottom to top, I am also moving bottom to top. That's why I am in the same direction of current. So across the resistor the current drop will be, voltage drop will be IE. Then if you write VBE, then you see this is negative positive, and I am moving across a voltage source. Negative positive means it is positive VBE. If I will move through this branch, VEB means positive to negative, then what I will write? Minus VEB. So minus VEB is same as plus VBE. Okay, then IBRB, here the current is IB and the resistor drop IBRB, and the current direction and my direction both are same. I am moving from here like to the VCC. Okay, then after IBRB there is a voltage drop which is nothing but VCC. Now you see this voltage drop is written minus VCC. What does it mean? It means after the collector terminal a voltage source is connected. This is minus, this is plus. Whenever a negative sign shows means first the negative terminal is connected. Okay, and now I am moving in this way. You see this is my direction. I am moving bottom to top. Then what I will write for this? It is nothing but VCC. So as I am moving from negative to positive, I will write plus VCC. Okay. So from this equation, what I have to find? Everywhere I have to find my IB. So for IB I have to eliminate this IE. So how I can eliminate? By substituting IE is nothing but beta plus 1 IB. Then our IB will become VCC plus VB. You solve this one. Only in place of IE, replace beta plus 1 IB. Then we will get IB equation. Okay. Now for the output loop, similarly I will move from here. I will move through this resistor and to the VCC. Then this is ground voltage 0. Then voltage drop is nothing but IE. Then minus plus VCE, and I am across a voltage source. I am moving negative to positive. Negative to positive means plus VCE. If I write in terms of VEC, then I am moving positive to negative. Then I will write minus VEC. So our minus VEC is same as plus VCE. Then voltage drop across the RC is nothing but minus RC, because my collector current is upward and my direction is also upward. That's why minus ICRC. Then this is the source, negative terminal first, then positive, and I am moving from negative to positive. That's why plus VCC. So from here also we can get the value of if I put the value of IE, IC, because as our base current is very minimum, so our IC and IE both are approximate to equal. So from there I will get my VCE. Okay. So all the 6 configuration, all these 6 configuration that we read for our PNP, for our NPN is same will be applied for our PNP transistor. Now we will see how our BJT can be act as a switch. Actually our BJT can be applied many applications. You see here I have written this point. A BJT can be used in many circuit configurations, such that it can be used as an amplifier, means to increase the strength, to enhance the its amplitude. Then it can be act as an oscillator, also act as a filter, rectifier, or on-off switch. The switch that we are using in our daily, in our home, that this transistor can be used for that switch also. Switch means it will shift from on to off. Switch, it will change its state. Okay. So if the transistor is biased in the linear region, we know our transistor operate in 3 regions. One is linear, second one is saturation, third one is cutoff. So when our transistor will operate in linear region, it will act as an amplifier. We will see how in linear region our amplification does. And when our transistor will operate in cutoff and saturation region, it will act as a switch. Okay. Now see this point. If the transistor is biased into linear region, it will act as an amplifier, or if it will saturate in cutoff region, it will act as a switch. Okay. So you will see with an example. So this is a symbol, circuit symbol. This is which type of transistor? NPN, not pointing in. Not pointing in means pointing outside. That's why not pointing in. So it is an NPN transistor. So here I applied one input. Here is a one VI. Okay, this is the input signal that is applied, and across the collector I will take the output. So we will see how when a 0 voltage is applied to this configuration, we will get a 5 volt, and what will happen if I will apply a 5 volt, I will get 0 volt. How? Okay, so when a 0 voltage, V in means 0 voltage, it is the 0 voltage that is applied. So this is the 0 voltage. Okay, this 0 voltage is applied to the V in. Our base emitter junction is reverse bias. How? You see, this is our base emitter junction. If our base will connected to the 0 voltage and emitter is a bit higher voltage, that means the P side is connected to the negative terminal of battery and the N side is connected to the positive terminal with some higher potential. That's why it will act as a reverse bias. This junction. Everywhere, what is a saturation or cutoff or linear? How it will vary? Based upon our configuration, based upon our connection for these two regions. One is emitter to base junction, one is collector to base junction. So as they will become forward and reverse bias, our region will change, our mode of operation will change. So when this base is negative connected to negative N side, that is emitter, connected to positive, means that is in reverse bias. And we know when our base emitter junction is in reverse bias, that is at cutoff region. What is the condition for cutoff region? This should be reverse bias, this should be reverse bias. Okay. Now, as this base emitter junction is reverse bias, then what will happen? It is reverse bias means there will no flow of current. For that, it means there no flow of current means from that IB, that from that base, there will be no flow of current. So when the BJT is in cutoff, the circuit ideally has the following values. So no collector, no base current means no. This is reverse bias, means base current equal to 0. When IB equal to 0, our IC, which is nothing but, you see, base emitter junction is reverse bias. As this is reverse bias, there will be no current flow, means our IB equal to 0. As our IB equal to 0, our IC is nothing but beta IB. That will be also 0. As our IC equal to 0, then we will enter in, this is for the cutoff region, and for the cutoff region our IC equal to 0, that we will see here. You see, for this cutoff region our IC equal to 0, and this is the from the characteristic graph, output characteristic, this line shows me the for the cutoff region. The below this region below the line shows me the cutoff region. For here my IC equal to 0 for this region. As our IC equal to 0, what is our VCE? That is collected to emitter voltage, that is nothing but highest voltage, which is nothing but VCC. How it will form? We know the equation for this characteristic graph. VCE is nothing but VCC minus ICRC. As this IC will become 0, this ICRC will become 0, then our VCE will become VCC. This is for the cutoff region. So this is called open switch. Okay. Now, as a 5 volt is applied, as this 5 volt is applied, means this P side is connected to positive terminal of battery, N side with the ground or some negative terminal battery. It means it is in forward bias region. So it is in forward bias region. This will be also in forward bias region. As both will be in forward bias region, then in which region it will enter? It will enter in the saturation region, because we know for saturation region our both junction enter into the forward bias region. So transistor is driven into saturation region. So saturation region, what will happen? Here our VCE is nothing but VCC minus ICRC. So as in saturation region, this VCE will become 0. As our VCE will be 0, our IC, which is nothing but VCC upon RC. This is the maximum collector current. So your IC sat, that is saturation current, maximum current is nothing but IC is VCC upon RC, and our VCE is nothing but 0. So this is the region that is for our saturation region. Okay. So saturation region, our collector current is maximum, but our VCE, that is collector to emitter voltage, is 0. Now this level of IB in the active region means our base current for this active region. This is from here to here. This is the active region. Okay. So for in this active region, at the edge of the saturation and active region, what we can define our IB max, that is base current, that is maximum base current. The level of IB in the active region just before saturation means it is the active region, it is the saturation region. So we are talking about the edge. So at the edge our IB max will become IC sat upon beta DC. This is the amplification factor that we know for a common emitter configuration, current gain. So this is IC sat upon beta DC. So how will came to know that our transistor is enter into saturation region? This is the maximum value. So as our IB will just increase than this value. As our IB will increase than this value, then we will came to know that our transistor is enter into the saturation region. You see, for different value of IB, we have drawn the characteristic. this is 0, IB equal to 0. This is IB 10, 20, 30, 40, 50, 60. Here IB is in microampere range, IC is in milliampere range. So you see, as our IB value is increasing, it means my transistor is entering in saturation region or not, as IB value is increasing. So from this point, our IB should be greater than equal to IC sat upon beta DC. If this condition occur, then we will come to know that our transistor is entered into saturation region. So if now see this configuration, now here I am applying this 0 voltage and 5 voltage. So as our IB value, what will happen? If our this 5 voltage is applied, then our IB, what I will write? We know this is fixed bias configuration. So for fixed bias configuration, our IB value is nothing but VCC minus VBE upon RB. Okay, this is for the fixed bias configuration. So we will apply our VCC, or for the input side, here the VCC is nothing but our input voltage. You see, this is VCC means here the VCC is different, this is different. Here the voltage that is before base is nothing but VI. So that is VI minus VBE upon RB. So that's why I have written VI minus VBE upon RB. So what is the voltage that I am applying now across my input side, which is nothing but 5 volt. So 5, and we know the VB value is nothing but 0.7. So 5 minus 0.7 upon, for this particular question, the RB value is given, that is 68 kilo ohm. Okay. Then we will get our IB value is nothing but 63 microampere. Then we have to check this condition. So for that we need IC sat. So IC sat is nothing but VCC upon RC. So our IC sat will become VCC value that we know from this question is nothing but 5 volt, and RC is nothing but 0.2 kilo ohm. So if I will put, I will get my IC sat is nothing but 6.1 milliampere. You see, this is milliampere range, this is microampere range. Now for this particular question, our HFE, what is HFE? H is nothing but for a hybrid, F which is nothing but for forward current amplification, E which is nothing but my fixed emitter configuration. Okay, that is nothing but our beta. Capital written, it is capital means it is beta DC. When it is written f small e means beta AC. That is change in del IC upon del IB. That is beta AC. Our beta DC is nothing but IC upon IB for DC values. So here HFE, that is nothing but beta is given 125. So I will put in place of IC sat upon beta DC, which is nothing but 6.1 milliampere divided by 125. So I will find this value is nothing but 48.8 microampere, and our IB value is nothing but 63 microampere. So I have to check this condition whether my transistor entered in saturation region or not. So our IB value, which is much greater than 63, is much greater than 48.8. It means it is satisfied. Means my transistor entered in saturation region, and my saturation region, what will happen? In this maximum current will flow. Okay. So certainly any level of IB greater than 60 microampere will pass through a Q point on this load line that is very close to the vertical axis. What does it mean? As we came to know, this is entered in saturation region. So each and every value, this is 50, this line is 50, this line is 60. Okay, for IB value this is 60 microampere. As we will increase our IB value, any value beyond 60, it means that line will touch this Q point. This is the Q point. As I will draw another value for IB, which is nothing but 70 microampere, then I will write, I will move like this. So as I will move like this, this point will, this 70 line will touch my Q point. As I will write for 80 also, this 80 line will also touch my Q point. That's this point is saying any level of IB greater than 60. As this condition once satisfied, any value of IB that will pass through the Q point. Now, this is for the when V input is 5 volt. Now when this V input is 0 volt, when this V input is 0 volt, 0 voltage or very small minimum value 0.7 volt, that is across this VB. If this that much voltage is applied, if my V input is applied 0 volt or this is 0.7 volt VB value, then what will happen? I will put in place of IB equation 0.7 minus 0.7 upon RB, because now I have taken my input is nothing but 0 volt or very minimum value 0.7 volt. Then what will happen? My IB value will become 0. As my IB will become 0, my IC value will also become 0. And here we have neglected the collector to emitter with base open. We have neglected this current. This is a minimum current. Such means very minimum current because of temperature. IC is 0. We have neglected this value. Then as our IB will become 0, then IC is nothing but beta IB, which is become 0. As our IC is 0, if you will see, if our IC will be 0, then what will we drop across this resistor? ICRC, that will be 0. Yes or not? As our IB 0 means IC 0. IC equal to beta IB. IB 0, so beta times 0 means IC 0. IC 0 means ICRC. This value is also 0. So our VCC minus 0 voltage. Then what will remain at the output? At the output, I will get my VCC. So when a 0 voltage is applied, when this 0 voltage is applied, then we will get a maximum of 5 voltage because there is no drop across the resistor. That's why I am getting a 5 voltage. And when applying a 5 voltage, there is a very minimum current, that is where it is written. This IB value, that is 0. IB value is maximum, and that I am getting maximum saturation current. That's why for 0 voltage, for 5 voltage, my output is coming 0. Why output is 0? As this collector current is maximum, then what will happen? My VCC minus ICRC. This is VCC. As this collector current is maximum, this ICRC will also increase. So VCC, a high value 5 minus this value is also nearly equal to 5. So 5 minus 5 is approximate to 0. 5 minus 5 equal to 0, or a value might be something 0.2 or 0.3. So this 0.2, 0.3 is written as a 0 voltage. Okay, so when a 5 volt is applied, I am getting each and everything is dropped across the resistor, so I am not getting an output. So across the collector, the VC value that I am getting 0 or very minimum value. And when a 0 voltage is applied, there is a no drop across the resistor. I am getting maximum voltage drop across VC, which is nothing but our VCC. That's why I am getting 5 volt. So it looks like a switch. So here it is, means it is inverting. 0 for 0 it is 5, for 5 it is 0, and for 0 it is 5. It looks like an inverter. Okay. Now just some points. When this 5 voltage is applied, then our current is high, and our current is high means our VC is very low. What does it mean? Let me show that equation. Okay, this is our VC equation, which is nothing but VCC minus ICRC. As this IC value is very high, so VCC minus ICRC, this value will also increase. This value will increase. So VCC minus a high value increase, it will give me a very less value. That means our VC value I am coming very slow. That is very low means it is very less value. So for this VC, what will become? There is a resistor. So this is the NPN transistor. This is collector, this is emitter, and across the collector emitter there is a resistor. Okay, so we are assuming this resistor is nothing but R sat. So this R sat is nothing but VC sat upon IC sat. This value is very less. Very less means when our input is 5 voltage, this resistor can be act as a short circuit, means a 0 ohm is applied. Okay, it means for for this type, this question, that our VC sat that we found from here is nothing but our 0.15. okay, so we know our VC value, that is a voltage drop across this collector emitter, is written 0.2 or 0.1. we took in this range, so let's take approximate value which is nothing but 0.15. and our our IC sat that we found from here, our IC sat that we found is nothing but 6.1 milliampere. So 0.15 upon 6.1, which will give me a value 24.6 ohm only. This resistor is only very small value, because everywhere for this question you see the resistor values that we took in the range of kilo ohm. This is kilo ohm, this is kilo ohm. So along with this kilo ohm, there is a resistor which is very small value, means only ohm. So this value can be approximate to 0. That's why for this, when 5 volt is applied, then our resistor value will be very less, that can be approximate to 0 ohm. Okay, it means it is a short circuit. And when, so this is the short circuit condition for this across this collector emitter. This is short circuit. This line will be touched to this point. This is point 1, this is point 2. This will be come to the point 2. And when an input of 0 voltage is applied, then what will happen? Our R cut off, it is in saturation region. That's why I wrote R sat. It is in cut off region, R cut off. So R cut off, it will become VCC upon ICO, because for cut off region there is a very small current. There will be no IC value, but because of temperature there will be very small current, ICO 0. Okay, and we assumed here the ICO 0 is very minimal or approximate to 0 milliampere. So our 5 volt upon 0 will be give me a infinite resistance. Means at cut off region this terminal is open. That's why this terminal, this BJT can be replaced by this circuit. This one, this is 2, this is open. You see the arrow mark showing that this line is open. Okay, so for cut off this line is open, and for the saturation region this line is short. So this is the representation. Now You have seen this point also before, that is what is on and off time. So there are transistors that are referred to as switching transistor due to the speed with which they are switched from one voltage level to other voltage level. Means for off to on and for on to off it will take very less time. That's why a transistor is used as act and switch. Means if you will see in your home, if you will just on your light switch, then automatically within a fraction of second this light glows, and if you will on the fan switch, automatically our fan start rotating. It means it is not taking much time. So that's how a transistor can be used. So the total time required for the transistor to switch from off to on is called T on. So this is off, this is on, so this is T on. So how much will be this T on? Or T on is nothing but the rise time plus this delay time. We have seen what is rise time. The 10% of this value to the 90% is called the rise time. So you see this is the rise time from here to here. This is 10%, this is 90%. And what is delay time? That is a delay for this is the delay time. 0 to 10% is the delay time. Okay. So our on period T on is nothing but TR plus TD. Similarly, for a transistor to off, that is for a on state to off state, it is called T off. T off is nothing but TS plus TF. This is fall time. That is 90% to the 10%. That is fall time. And what is TS? It is storage time. This is the storage time. This is the transistor. The transistor need this much time for its storage. This is TS. So this TS plus TF will give me T off, and this TD plus TR will give me T on. Okay, so this is all about your transistor act as an switch. In the next class we will see how our transistor can be used as an amplifier.